Somewhere on the ocean right now, a cargo ship is moving. Her exhaust is almost invisible, her engine room resembling a clean laboratory. International shipping emits approximately 1 billion tons of carbon dioxide every year. If the global maritime fleet were its own country, it would rank among the world's top 10 greenhouse gas emitters, standing shoulder to shoulder with major industrialized nations. The International Maritime Organization has set a strict target to counter this: net zero emissions from international shipping by or around 2050. That deadline sounds comfortably distant, but the heavy cargo ships being ordered and built in shipyards today will still be sailing in 2050. The window to slowly adapt to this regulation is already closed. For cars and local delivery trucks, the answer is electrification, so it is entirely reasonable to ask why we don't simply put batteries into cargo ships and sail them on electric motors. The answer comes down to what maritime engineers call the energy density problem. The energy stored in a single ton of heavy fuel oil is staggering. This cross-section shows the physical limitation. To match the power of fuel oil with current battery technology, you would need a mass of lithium cells so enormous it would consume the ship's entire cargo capacity. A vessel carrying only its own batteries is useless for global trade. The industry has to find a chemical alternative that packs the intense power of oil without the carbon emissions. The first serious alternative adopted at scale was liquefied natural gas, or LNG, cooled to minus 162 degrees Celsius so it can be stored compactly on board. LNG burns significantly cleaner than oil and eliminates sulfur emissions entirely. But natural gas is primarily methane. When engines inevitably leak small amounts of uncombusted methane, a greenhouse gas roughly 80 times more potent than CO2, the climate benefits quickly evaporate. This brings us to the near-zero candidates, starting with green methanol. Major operators are already putting methanol-fueled container ships on the water. This flowchart illustrates how green methanol creates a closed loop. By combining renewable hydrogen with carbon dioxide captured directly from the atmosphere, the CO2 released when the ship burns the fuel is exactly the same CO2 that was taken out to make it. But methanol holds less energy than diesel. To make the exact same transoceanic voyage, ship designers must expand the fuel tanks, cutting directly into the space reserved for paying cargo. LNG solves local air pollution, but leaks potent methane, while methanol forces operators into a zero-sum game between carrying enough fuel to cross an ocean and carrying enough cargo to make a profit. To eliminate carbon from the exhaust entirely, we have to look at ammonia. Because the ammonia molecule contains zero carbon, burning it exhausts only nitrogen and water. But ammonia is difficult to ignite, and it is highly toxic. A leak reaching just 300 parts per million in a busy port or a sealed engine room would be lethal to the crew. Beyond ammonia lies liquid hydrogen. Fed into a fuel cell, it generates heavy propulsion while exhausting nothing but pure water vapor into the sky. Yet hydrogen presents the ultimate logistical hurdle. It must be stored cryogenically at minus 253 degrees Celsius. It is so exceptionally light that storing enough for a deep-sea voyage would require tanks larger than the hull itself. The chemistry of marine propulsion presents a brutal trade-off. The closer a fuel gets to zero emissions, the more toxic, voluminous, and difficult it becomes to handle in the physical world. Because no single chemical fuel is perfect, engineers are supplementing modern engines by returning to maritime history's oldest power source, the wind. This overhead schematic shows how a Flettner rotor works. As the wind hits the spinning cylinder, it exploits the Magnus effect to generate a forward force that literally pulls the steel ship through the water. These hybrid technologies do not replace the diesel engine, but by harvesting free aerodynamic thrust, they can immediately slash a vessel's fuel consumption by up to 30%, buying the industry time while the chemistry scales up. All of these overlapping technologies converge here. Shipyards are laying the keels for the vessels right now that must survive in a 2050 world that does not fully exist yet. To survive this transition, operators are installing complex dual-fuel engines. These allow a ship to run on an alternative fuel when the green infrastructure is available and switch back to conventional oil when it isn't. But beneath the steel and the emission targets, this transition relies on an invisible human workforce, managing these experimental systems in the middle of the ocean. A mechanic who has spent decades working with heavy fuel oil must now be rapidly retrained to safely manage cryogenic liquids and highly toxic gases. Massive shipping conglomerates have the capital to invest in these advanced fleets and specialized training, but smaller operators in developing nations, running older ships on thin margins, risk being priced out of global trade entirely. Reaching net zero emissions means little if the transition breaks the human workforce operating the systems or severs the global trade routes that developing economies rely on. The perfect vessel that will carry the world's cargo in 2050 has not yet been built. It will likely be a hybrid, harvesting the wind with mechanical rotors, burning zero-carbon chemistry, and maintained by a crew of specialized chemical handlers. We have been building ocean-going vessels for 5,000 years, from timber to iron and sail to steam. But the engineering decisions made in this specific decade will dictate the shape of the global fleet for the rest of the century. The blueprints being finalized in design offices right now lock in the carbon footprint of global trade for the next 30 years.